The NoC-SE Setup tab is starting point for configuring Network-on-Chip Synthesis Engine, or NoC-SE. It contains the global settings that control how NoC-SE performs synthesis. Note that this has no impact on the MCN part of the SI-L1 and only for NoC part. The general selection defines the overall synthesis strategy. More details for each setting can be obtained from the tooltip here as well. You can also check SI-L1 tooling section of Configuration and Integration Manual for details on each configuration option for all NoC-SE tabs. Enabling Use Traffic Parameters displays the Traffic section. This option determines whether NoC-SE uses traffic information during synthesis. The traffic settings control how NoC-SE interprets the traffic specification and which traffic-aware optimization algorithms it uses when generating the topology. Next, enabling Use Timing Parameters display the Timing section. This option determines whether NoC-SE considers time enclosure during synthesis. The timing settings define how NoC-SE generates a network-on-chip that is physically implementable and capable of meeting timing requirements. Microns per nanosecond is an important parameter because it tells NoC-SE how far a signal can travel on a silicon in 1 nanosecond. For example, a value of 8 micron per nanosecond means the signal can travel 8 micron in 1 nanosecond. With 400 MHz clock, which is 2.5 nanoseconds period, a signal can therefore travel about 2000 micron in 1 clock cycle before requiring a pipeline stage. In our design, let's enable both Use Traffic Parameters and Use Timing Parameters, and leave the remaining settings at their default values, so the synthesis engine will create a topology which fits both our traffic and timing requirements. In the bottom left corner, the physical floor plan pane allows you to define the chip's physical layout and specify routing constraints for the network. Once we finish, let's save the configuration by going File and clicking Save. Next, let's configure basic traffic. At a high level, basic traffic defines the communication characteristics for every source and destination pair in the data network. The Traffic Profiles pane on the right lets you define one or more traffic profiles. For this example, we will create a separate traffic profile for each ASNI. Click on the plus icon and the dialog box will appear. Each profile includes the following parameters. The average bandwidth specifies the typical sustained traffic rate, while the peak bandwidth defines temporary maximum traffic rate. The traffic class is used for traffic isolation. The latency sensitive option indicates whether NoC-SE should prioritize latency when generating routes. You can also specify the average read and write transaction lengths. Finally, the options to minimize clock domain transitions and minimize power domain transitions instruct NoC-SE to prefer routes that cross fewer clock or power domains. Let's start with ASNI 0. Both ASNIs use 128-bit data width and operate at 400 MHz, so let's set the peak bandwidth to 51,200 megabit per second and the average bit to 42,000 megabit per second. Let's assume that most read and write transactions use 16-bit bursts. Next, let's create a second traffic profile for ASNI 1. We will use the same peak bandwidth of 51,200, but reduce the average bandwidth to 25,000 megabit per second. For this interface, let's assume that most transactions use 32-bit bursts. Finally, we can assign appropriate traffic profile to each source and destination pair for both read and write traffic by clicking the gear icon on the traffic metric editor cells. Let's quickly assign the rest of the source and destination pairs. Once we finish, let's save our configuration. Next, let's look at the advanced traffic. At a high level, advanced traffic allows you to model real system operating use cases instead of assigning a single average and peak bandwidth to every source and destination pair. This provides NoC-SE with more realistic representation of how traffic behaves under different workloads. On the left, the PAN scenarios PAN defines groups of communications that are active at the same time. For example, let's create a path scenario named PS0. If you tick the box next to the read and write on the source interface row, the percentage field below the boxes become valid, and destination interfaces that are accessible by these source interfaces are listed below. In this scenario, ASNI0 writes to AMNI0 and AMNI1 using 100% of its interface bandwidth, while ASNI1 writes using 20% of its interface bandwidth. Next, let's create a second path scenario named PS1. In this scenario, ASNI1 reads from the CMNI0 and CMNI1 using 45% of its interface bandwidth and writes to both interfaces with 75%. On the right, the traffic use cases PAN lets you group one or more path scenarios that occur simultaneously. A design can contain multiple use cases. However, only one use case is considered active at a given time. For this example, create a use case that includes both PS0 and PS1. When NoC-SE performs synthesis, it analyzes the combined traffic from both path scenarios because they are active at the same time. Once we finish, let's save the configuration. Next, let's configure the HLS floor plan. In this tab, we define the floor plan so that it matches the physical layout of our design as closely as possible. The information you provide here tells NoC-SE where the die blocks are located, where routing is permitted, where routing blockage exists, and what physical constraints the synthesis engine must consider. This tab uses the same view as physical canvas, which we will cover later in the training. Throughout this video, I will refer to the central editing area as a canvas. The red square is our die, with the size that we have configured previously during the NoC-SE setup. Before we begin, let's move the floating canvas toolbar so that it does not obscure the left pan. This toolbar contains the tools used to edit the canvas. If you hover over any tool, a description of its function is displayed. We also have Interconnect Architect Canvas Tools video, where functionality of each of these tools are explained. You can check that video out after this one. Starting with the left pan, the first section is Setup Boundary. Here you define power domain boundaries and, if required, subsection boundaries for finer physical partitioning within a power domain. These boundaries define physical regions that NoC-SE uses as placement and routing constraints during synthesis. Let's create the power domain boundary as an example. Click Add Power Domain, select the appropriate power domain, and specify the starting X and Y coordinates, along with the width and the height of the region. Then click Add. The power domain boundary PD0 now appears as a gray region on the canvas. You can mouse scroll to zoom in and out, and click the mouse button and move the mouse to pan as well. Now, let's click Next to expand design process high-level specification controls. In the floor plan elements pan, you can add die blocks, interfaces, and memory controller nodes. Drag a die block onto the canvas to represent a part of the system that contains one or more of the interfaces you created earlier. When you select the die block, the property editor opens on the right. Here you can modify properties such as a block name, location, size, associated power domain, and assigned interfaces. At this stage, the die block is not associated with interface. To associate one, drag the required interface from the left pan and drop it onto the die block. Repeat this process for each remaining interface in the design. Before adding the AMCNs, let's make the CHI network visible.
In the Canvas Visualizations pane, locate the visible network and select Chi. Otherwise, once we add MCN to the canvas, it will not be visible. Now add the MCNs to the canvas. Unlike interfaces, MCN do not need to be placed on top of a die block. Drag each MCN directly onto the canvas and position it as required. Once we finish, let's save our configuration. Now that we have completed the NoC-SE configuration, we are ready to run NoC-SE. During the synthesis, NoC-SE uses the requirements you have defined throughout the configuration process to generate a network-on-chip topology that satisfies those requirements as much as possible. Before starting synthesis, it is recommended that you run the HLS design rule check to verify that high-level specification is valid. There are two ways to start NoC-SE. The first is from the Floor Plan tab by clicking Run NoC-SE button. The second option is from the Run NoC-SE tab. Both methods perform the same synthesis and produce the same topology. However, the Run NoC-SE tab also displays the synthesis log, making it easier to monitor the process and diagnose any errors that occur during execution. For this example, we will run NoC-SE from the Run NoC-SE tab. When the synthesis completes successfully, a green checkmark appears next to the Run NoC-SE, indicating the topology has been generated successfully.